Hey everyone, welcome back. Good morning. About 4 minutes, and then it'll be 9. But hope y'all are having a great week. Happy Halloween for you guys celebrating this weekend or even today. But yeah, good to see everybody. Feel free to say hi. But yeah, we do have 3.5 minutes, and then we get the lecture underway. Good morning, Kelly. It's kind of a little overcast weather where I'm at here. A lot of clouds, a lot of fog. Probably a good thing, I guess, with the fire. But yeah, also nice to have a little fall weather. Bust out the fall wardrobe, sweaters and things. Hey, Senna, good to see you. Good morning. Hey, Eva. Hello. Hope you're having a good start to the day. Just another minute, pretty much. Welcome to class, everyone, showing up and arriving. Appreciate you guys' attendance as usual. Hey, Anthony, good to see you too. All right, guys. Well, that's pretty much 9. Hey, Drew. Always good to see you. Yeah, so welcome back. We've got another interesting and important meeting lined up for today. We're just continuing to work through this new topic that we've started on last meeting, which is time, metaphysics of time. What is the current scientific consensus view of time in physics? So we started that whole discussion by looking at the writings of the world famous scientist, physicist, philosopher Albert Einstein. So I'm just going to recap a little bit of what we did talk about there, and then I'm going to add a couple of more concepts of theory of relativity for you guys to ponder. So basically, all right, Einstein in 1916 wrote this book called Relativity, and the goal behind the book was to try and present the theory of relativity, the general and special theory of relativity, to a wider audience, and to try and provide, explanations and examples that would be somewhat more comprehensible to an average person who's not necessarily got a lot of technical knowledge about math, physics, and so on. So in relativity, there's a section that our textbook has reprinted, and they retitled it Time and the Relativity of Simultaneity. So the first thing that Einstein discusses in that piece of writing, this is just my recap summary of last lecture. First thing he discusses is that suppose that there's two lightning strikes that occur along two different points of a railway embankment. So one is on the left, call it lightning strike A. The other one on the right, let's say that's lightning strike B. And he asks what at least initially appears to be a straightforward, easy to answer question. Suppose they happen simultaneously. Question, what does this mean? What does it mean to say that the two events are simultaneous? And he realizes that any attempt to define the concept is very hard to do, because essentially you're tempted to give a circular definition. And he knows that some people might try to just resist any effort to give a definition of it. Like, for example, someone may think the concept is clear enough. Maybe we don't have the ability to exactly define it, but we use the word simultaneous, and when we do, everyone seems to understand what we mean. So is there really any need for a more specific definition? And that's where Einstein cuts in and says, sorry, but no, we have to have a more precise definition than something that's just vague, unstated, ambiguous. If you're a physicist or a scientist, you have to have a definition of an operational concept that is so precise that you could test whether or not the concept had been fulfilled in a given case. So he says, we might not actually have any concept of simultaneous unless we have the ability to test the proposition that two events are simultaneous. So now his question is sort of a little bit refined, and it is, what would be the way of testing to see that these two lightning strikes occurred at the same time? So he says, actually, there is a way of testing this, and here's the proposal. Let's place an observer standing still, standing motionless, at the exact midpoint M, which is the point that bisects the line segment AB. Okay, and so if this guy's at M, then he's equally distant from the first, well, one lightning strike A, and he's also just as far away from the other one, B. Now, if we assume that the speed of light is constant and fixed, so that it never differs its rate of travel, it's always the same velocity. If we assume that that is the case, then a man who's standing at M, who witnesses the two events in the same moment, in the same field of vision, we could infer based on that the two lightning strikes emitted from their origin points at the same time. Because it's kind of like, if you've done these old math problems, if you have two things that have moved at the same velocity and they've traveled the same distance and they converge on a common endpoint at the same time, that means that given that they have gone the same distance at the same rate of travel, arriving at a common endpoint, they must have left from their two departure points at the same time. Okay, we have to stipulate that the speed of light is constant to arrive at this result, but Einstein says this is no problem and we could do that freely. So now we have our definition of simultaneous. If there is an observer who's able to see the light signals from two things reach him and his visual system at the same moment, we could define the two events as simultaneous with reference to him. But it gets very strange when we start to imagine what to say if there are two observers on the same scene and they have different states of motion. Okay, so now we imagine that this second observer is traveling along a train on the train track itself. And he's moving with constant velocity, some rate of travel, call it velocity v. So if he's moving with constant velocity v along the train track, and he intersects with the midpoint M, and as seen from the train, let's define that as M prime. So while he is riding along on the train and he hits M prime, the other guy who's currently standing still at M, they're aligned along that plane. And the man who's standing still, as we described, will see the two lightning strikes happening simultaneously. But for the one who's moving, he doesn't stand still. And so although he breaks the plane of M prime while the other guy's doing his observation, he doesn't stay there. He keeps moving over towards the right, towards B. And so because he's moving, the two light signals, which are each traveling at the finite but very fast speed of light, they can't reach his eyes at the same exact moment in time. If he had been standing still at M, just as the other motionless observer is, then that would have happened. But since he's running towards B and away from A, he will receive the light signal from B first, and then just subsequent to that A. So in the experience of the second observer, the two events are not simultaneous. B happens initially, and then second after that is A. And if we added a third possible observer traveling in the opposite direction towards A away from B, passing by midpoint M double prime, then that observer would have a yet different experience of the two events, seeing A happening first and then B for the same reason, but just flipped to the other side. So when you really consider the deeper implications of this, it's very, very far-reaching and trippy and kind of deep, because it means that the order of events, which normally you take to be linear and objective, is not at all. It's relative. So what order do the two lightning strikes happen in? Is there a fact that they're simultaneous? Is there a fact that they're not? There's no fact of either kind. It depends on the condition of the observer and their state of motion relative to the observed events. And so it's like everyone has their own personal time defined by their relative state of velocity compared to other observers and objects in the universe. Such a strange idea, because in your own view, you think that there's a defined, very clear ordering of events, and it can't be rearranged. Like before, you were that little baby that you see in your child pictures. Currently, you're this college student. In the future, you know, whatever, you'll be a little older, elderly person. And you think that these things are lined up in a particular order and there's no way of reconfiguring them. But basically, according to this theory of space-time, we have to grant reality to the moments that, relative to you, are considered to be future moments. Because depending on the position the observer is in and their velocity, they're able to observe any of the events that happen in the whole space-time framework. So it kind of implies this very deep thing, which is that all the events and all the moments, inclusive of the past, present, and future, are all equally real. They all exist. And therefore, the kind of real weird thing is, why is it that our consciousness seems to perceive them in this linear ordering, if that's not the sort of physical reality? And that's like, you know, a puzzling question, very deep. But I wanted to add a little bit more information for you guys about some further implications of the relativity theory of Einstein. There are at least two more things about it that are really weird and interesting, and I kind of wanted to discuss that with you too. Okay, so what I want to mention here is what's called the idea of a light clock, because this is what is able to explain to you the concept of time dilation. All right, time dilation is a real physical phenomenon which is proven by Einstein's theories and which has been physically confirmed through empirical experiments and tests. So it's a real thing. It's very, very weird. Time dilation. And to explain time dilation, we need this example of the light clock. Okay, so I'm going to try and explain this by means of just a few diagrams and pictures that I will draw here on this board. So a light clock is a device that can be used to measure time. And it uses the consistency of the speed of light that a photon travels at in order to use that as the time measurement. So imagine that we have two planes of mirrored glass. That's what these two things are. So mirrored surface, top mirrored surface, bottom mirrored surface. Suppose then that we take a photon beam, right, and we excite the photon and we shoot it towards the top mirrored surface, okay? So photons of light, as you guys understand, they reflect off of a mirrored surface. That's why when you look in the mirror, you know, you're seeing the light rays that are reflected off of its surface and they're showing the image of whatever is in front of the mirror. So this photon goes up and it gets fired towards the top plane of the light clock. Because it's reflective, it bounces it back down, okay? And because this is also a mirrored surface, it bounces it back up. So basically now you have this bouncing photon in the light clock that just keeps oscillating between the top surface and the bottom surface at an exactly constant rate, because the speed of light is constant, fixed, and it never alters at all. So let's suppose that we now make this a time measurement device. So with each cycle that it completes from top to bottom, let us just assign that the value of being 1 second of time. So if you're an observer watching the light clock, you just see this up and down in between the two planes beam of light. And it's counting seconds for you. 1, 2, 3, 4, okay? And it just goes perpetually like that. You got that idea, that picture in your mind? I mean, I'm trying to explain it with words, trying to give you the slight visual to assist, but that's the idea of a light clock. Okay, now, I want you to imagine this extension of the example. Let us suppose that we have 2 light clocks and an observer, all right? So this is light clock, let's say, well, actually, I want to make the bottom one a little bit different, so let's recreate light clock 1 up here. And this is the photon beam bouncing. And here's light clock number 2. And here is this observer who's able to just watch the 2 light clocks as they move. Now, light clock number 2 and light clock number 1, we're going to introduce a difference between the two. Light clock number 1 up here, let's say that it remains standing still. So it stays in place motionless, positioned in front of this guy. So they're both, you know, he's standing still, he's with the light clock, it's not moving, and he's just watching the photon beam go straight up and down. That's light clock 1, the top one. But this bottom one, okay, what we're going to do with it is we're actually going to accelerate it to the right very, very fast, maybe even close to approaching some percentage of the speed of light. So now that's being shot over to the right, the second light clock, very fast with a high velocity v. Okay, now the photon beam. I have not yet drawn the line which describes its path of motion between the two planes. But I want you to tell me how I should draw that line if we assume that it's being observed by this motionless observer who's standing still while this light clock gets accelerated fast to the right. Okay, now I want you to imagine a difference between the angle of approach that the first light clock will have as it bounces between these two planes, and the angle of approach that will be observed by the motionless observer of the second light clock, which is now being accelerated very quickly to the right. So, Jason, you say up and to the right. Okay, good. In other words, don't you mean like a diagonal, correct? This one's going to be straight vertical, up, down, every second, one cycle. But this one's sliding with such velocity that it's going to, as you've said, Jason, appear as though a diagonal arc of approach, you know? Because it's moving that fast, the viewer who stands still will see as though it's moving at a diagonal. And that stretches out and elongates the length between each cycle. Can you sort of see that idea if you just visualize it? This one approaches a diagonal, and the faster that it's going, the more gradual does the angle of approach appear to be, okay? But this one, which is standing still with him, just keeps looking as though it's bouncing up and down. Now, let's assume that these two light clocks are perfectly synchronized, right? They've been created at the same time, and they record time in unison. So when the two of them are standing still together, they both just look like they're bouncing in unison, straight up and down. But once one of them gets accelerated over to the right, it's now going to appear as though a diagonal to a motionless observer, okay? Because the wavelength of the photon gets stretched by the velocity relative to a motionless observer. Now, if this observer was traveling with the light clock, right, and he's like riding along with it going very fast, since he then shares its velocity and state of motion, he then does not see any diagonal approach. It just appears to be vertical yet again because he's part of that frame of reference then. Okay, so in this situation, which of the two light clocks, let me add one more thing before I ask you this question, okay? So suppose that we let this one accelerate to the right very fast, and we allow it to go in that direction for quite a while, maybe orbiting the Earth at that super fast speed. After a while, we allow it to stop and return back to rest, and we reunite it with its twin light clock and this observer. So now they're all back, sitting together, standing still. Which of the two light clocks will have recorded fewer seconds? Or you can say, which one will have recorded more seconds after they've been reunited? Which one has taken more time? And which one has taken less time? You've got two light clocks. the angle of approach of the photon appears differently to the one observer based on the one being in motion and the other one not. So I'm just asking you, which of the two is the one that has recorded? Jason, is your answer light clock number 2 would be slower? Yes, Drew, and yes, Jason. Yes, the one that is accelerating in fast motion elapses fewer seconds because it simply takes a longer trajectory for it to complete one cycle of going from top surface to bottom surface, right? Because this only has to go the slight up and down trajectory of a vertical path. But this has to cover a whole diagonal, and depending on how fast it's going, that diagonal will be stretched even more. So it's very weird because now when they get reunited, this one, relative to the motionless observer, has fewer seconds recorded than this one does. So these two light clocks, which were issued at the same time, which are running in synchronicity, which are in unison with each other, synchronized, they no longer display the same amount of time passage. This one basically has gone through more time than this one. And why? Just because one has a greater state of velocity than the other. And this is not at all like just some kind of phenomenon that doesn't capture the reality of the situation. Like there's really only one interval of time that has passed for both. It just looks like one has less than the other. No, no. The measurement of time itself depends on this state of motion. And so it's just a fact that one of the objects has passed through time slower than the other one. Because as you, basically here's the rule, as you move quickly through space in terms of speed, you're moving slower through time relative to other objects that have a lesser state of velocity. So fast-moving objects through space are moving slower through time relative to other objects that are moving slower than they are in space. So weird, right? Now, and it just keeps getting weirder. So suppose then that we have two observers, and this one we place on the light clock, and then the other one we leave with the motionless light clock, and we allow this guy to take a trip with the fast one. Okay, after he spins around, moving really quick with the light clock, you know, traveling through space very fast in this very fast-moving light clock, when he's reunited with his counterpart, he will have passed through time slower than his counterpart. And that is what gives rise to this very, very strange concept in physics, which is called the twins paradox. It's just basically the same idea here as this whole light clock example, except now we imagine it as applied to people. Okay, so you guys all understand identical twins, right? These are people that are siblings, which are born at roughly the same time. I have my sister and two brothers are triplets, so they're, you know, it's like 3 twins, right? But anyway, twins. If twins are born, they're the same age. That's all I'm saying. So now, suppose that we do this. We have our 2 identical twins born at the same time, and we place one of them in a very fast-moving rocket ship, like a interstellar space traveler, and we fire them off into space in that fast-moving rocket ship, going at huge speeds, maybe even somewhat close to the speed of light, as fast as we can imagine getting. Now, we leave the other twin standing stationary on the surface of the Earth. And so the one that's going through the universe very fast, they spend some amount of time up there, they come back down, and now when they reunite with their identical twin, what would be the case? Will they have the same age anymore? Or if not, who will be younger and who will be older? You've got 2 identical twins, but one of them now has gone very fast through space in like a rocket ship. The other one has not. So the space traveler and the Earth dweller are now reunited after some time. The one going fast will now be younger, exactly, Anthony. Now, how weird is that? Like, they were at the same age throughout their life, but now because one has taken on this much greater state of velocity, it's a younger person than their counterpart. And so this kind of gives you the real-world corollary to the concept of science fiction, like time travel. Time travel to the future could absolutely happen if there was just a way to build a device that could withstand these forces, accelerate at those speeds, and somehow a human body survive the process. But yes, it would be true that the identical twins would no longer share the same age. And it would, how much different their age would be, how much time dilation experience by the fast-moving twin would depend on how fast they were moving and for how long, okay? So, you know, suppose they were moving at a close fraction of the speed of light for a certain amount of time. They return back to the planet Earth. Now they are like 10 years younger than their identical twins. So time has moved much faster for the twin who has remained at rest or relatively at rest, and much, much slower for the twin that's been moving through space very fast. And this is kind of the basis for that like final scene of Interstellar. I don't know, did I mention that to you guys last time, talk about the film Interstellar? I might have made like a passing remark about it at the end of class, but if I had not, let me know and I'll remind you of this little plot point that definitely has relevance to this. Anybody? Because I have two sections. I might have said it to the other section. Interstellar reference, is that memorable to you, or maybe I didn't get it in? No? Okay, so yeah. I don't know if anybody's ever watched this movie. Maybe you don't even know what I'm talking about. But there was a film a few years back with Matthew McConaughey, a science fiction film called Interstellar. It was a pretty good movie. But, you know, it had a lot of these physics concepts from, like, Einstein's theory of relativity and quantum physics that, you know, they deploy for a popular audience just to kind of make some cool, interesting science fiction story. But all the things that were involved in the movie are at least theoretically possible according to science and physics. So one scene of the movie, and maybe this is a little spoiler, but whatever. In one scene of the movie, closer to the end, Matthew McConaughey, who's like playing the role of like a space traveler, you know, an astronaut that goes at these super fast hyper speeds through space, he comes back to the planet Earth, returning from a big journey, and he's now reunited with his daughter. But because of how fast he was traveling through space, his daughter is older than him now. And he's actually giving her comfort on her deathbed because she's like an older senior citizen in comparison to Matthew McConaughey. And how strange is that, right? To imagine that you have a child and this is a baby and you're an adult, and then you just move through space really, really, really fast. And then after having done that, your child is now actually leapfrogged and is older than you in terms of, you know, the rate at which they've aged compared with you. So it's just so strange. I mean, but that's actually something that would happen. And it's not speculation. It's not up for debate. This has been proven physically with actual tests. So like there's a couple of tests that have been done way back in the day before we had very powerful particle accelerators and stuff that we have now. They basically tested the proposition by having the two of the most advanced clocks that can record time way down to like the nanosecond scale. And they made sure that they were absolutely synchronized. And they would place one on some of the fastest moving objects that we are able to produce, like, you know, jets moving at several times the speed of sound. It's still far short of the speed of light, but, you know, Mach speeds. And after reuniting the two clocks, the mathematically predicted disparity between the two recorded amounts of time was exactly in accordance with what the result was that we saw. So that's one example of having actually proven this phenomenon with two clocks passing through time at different rates, depending on one having more speed than the other. And a more recent example of proof of the concept is through particle accelerators. So, you know, like a human body, we talk about the twins paradox. Let's accelerate one person very close to the speed of light, leave the other one at rest. Well, as much as that sounds like an interesting theoretical idea, it's probably going to be very difficult to ever, first of all, devise a machine that has the ability to travel at such velocities, right? But also just the forces of that you would expose a human body to would just rip you apart for the most part. And so it's hard to imagine this actually becoming a realistic thing to do. But what we can do it with are tiny little elementary particles. Okay, so in these big particle accelerators where we can fire tiny little atoms and stuff close to the speed of light, like at a 90+% of the speed of light. Then we can observe the time dilation effects as they affect the half-life of these little particles. And that yet again proves that the average life of one such particle before it decays is extended when they're moving that fast relative to other particles that are not shot at those speeds through the chamber. So it's very weird, but we do have empirical confirmation of it. Now, question. If time dilation is real, and it seems that it is, how come you guys think we don't notice it in our everyday lives? Like, how come people who, let's say, fly on airplanes, jet-setting types of people, how come we don't think or notice that they are passing through time much slower than all of the other people who just stay at home and not moving as fast? If this is true, then how come runners that are running, you know, like me every day, a lot of miles, are not passing through time slower than the people who don't have that kind of that exercise habit? Why do you think we don't notice these effects if they do exist in an everyday situation on the planet Earth? There's an answer to this, but I just wonder if you can infer it. Good, Anthony. It's such a small difference because we're not going that fast. That is correct. Yes, it's because to see these time dilation effects be something more than infinitesimal and therefore impossible to measure, for them to be measurable and macroscopic, you'd have to be achieving variable speeds with other observers that were on, massive disparities. Like you'd have to be capable of moving at appreciable speeds of the speed of light, but we don't have the ability to do that. So although there are some time dilation effects, they're on the nano scale, and we therefore don't notice them. We're essentially bounded on the surface of the Earth, and therefore all of us moving at roughly the same speeds. Like how much faster can I possibly go than you in the most advanced technologies that we have developed? If I'm on a rocket ship going to the moon, maybe I'm going like 10 miles per second or something when I really hit maximum speed. But that's still nothing close to the speed of light, which is 186,000 miles per second. So the time dilation effects, though real and measured and proven, are very, very infinitesimal and therefore not negligible in the ordinary course of human life. But if we did have the ability to travel at those hyperspeeds, if that actually was a real thing, then we would have all kinds of problems staying in synchronicity with our time. Like everyone's watch would be on a different time than everyone else's. People would be aging at different rates than other people, and so it would be, in a way, pretty messy, but that's exactly how it would work. Okay, so so I've talked to you then about the time dilation phenomena and the twins paradox. When you think about the concept of time travel to the future, it would be just as easy as, not easy, but it would be theoretically just as easy as having like a centrifuge which a person could enter, and then the centrifuge spins them around close to the speed of light. In that case, they wouldn't even have to go very far to achieve these very fast speeds. But of course, the velocities we're talking about would probably just rip them to shreds or whatever. But imagine that you enter into some kind of fast-moving centrifuge, and you exit it after like 10 minutes of time, your time, like as recorded on your wristwatch. But when you come out, it's been like, I don't know, year, 5 years, depending on how fast you're moving in there and how long you're inside. Travel to the past is a little more difficult to comprehend, but we will actually talk a little bit about that in some lectures that we have next week. And also maybe, if I have a chance, we'll talk a bit about it today because there's still a little more I have for you on Ted Sider. Okay, so then, next up, let's get into this new author on the same topic. So American philosopher Ted, or really Theodore Sider, but he's kind of known through the field informally as Ted. I think he was born in 1967. Let me just make sure I'm giving you the right dates. Okay, so Ted Sider, who was born in 1967, and he's still alive and well. So this here is from 2005, and it's a piece of a book that he wrote, but they have retitled it. The original book title was The Riddles of Existence, A Guided Tour of Metaphysics. But to make it an article that's sort of self-standing for this anthology, they just retitled it as Time. Okay, so Ted Sider, American philosopher, is the author, writing in 2005, and the paper is just called Time from our book. So, the article's goal is just to sort of provide the reader with basic explanation of what are some of the puzzles and problems philosophically that emerge when we start to think about the nature of time. What are some of the weird, puzzling, and paradoxical, almost bizarre aspects of it? So he starts by sort of noting that time is so fundamental to us that questioning its nature is difficult. It's something that we are so familiar with in our everyday lives, but because of that, we just kind of take it for granted. It's sort of like breathing. You're breathing every second, and it's an autonomic thing about your nervous system, so you don't have to think much about it. But if you stop to think about it, you're almost like, wow, now I'm paying attention to my breathing. It's like, am I breathing shallow? Am I breathing deep? It almost takes labor and effort to do. If you were a fish, you're swimming in the ocean surrounded by water all the time. Of course, this is maybe not the best example because fish are not the most intelligent of all creatures, at least most of them. But, if you were able to think like a human, you'd be like probably not too interested in the concept of water because it's something that you just take for a given. So time is sort of like that for us. We're swimming around in it. It's all around. We always think about it. We always are aware of the passage of time. But questioning the nature of it and thinking about it on a deeper level is quite hard. But he says that we should do that. We should try to dig in and, think about the deeper scientific and philosophical understanding of it, because the problem is that once you start to interrogate it beneath the surface depth, the ordinary idea that we have of time starts to kind of break down and not make as much sense. So one of the things that he says is kind of weird about time is that we always say that time passes, right? We talk about time moving, time passing. So here's kind of the first question that he throws out there for the reader to grapple with. People say that time moves. When people describe or discuss the idea of time, a common way of referring to it is to speak of it moving. How many different common sayings or phrases can you guys think of which express the idea of time somehow being in a state of motion? Has anybody ever heard a little saying like that, like time blank? And then the blank thing is something about like being in like motion, almost like a metaphor of physical motion. Well, people say life is short, but not really, that's not the point. The flow of time, yes, but people say time flies, yes. People say that time flies, people say that time passes, right? Passing is like a physical thing. Flying is a physical motion. People say time marches on, right? Like marching is to move through space. Sometimes people say that time is, time flies when you're having fun. Time is going so fast, right? Like fast, as though it has a velocity. Or sometimes when people are bored, they say, oh my God, time is taking forever. This is so slow. Time is passing very slowly, as though it's a rate of motion that can be either faster or slower. So what these different phrases and maybe some even cliche phrases express is that when the ordinary person thinks of time, they think of it as something that's somehow in motion. It's moving along, like as if it was a flowing river, and here we are, and we're just caught up in the flow of time, moving along with it. But the thing is, ask yourself, what are we saying when we say that time moves? The reason that that is problematic, and the reason that he poses this question for us, is because movement itself requires the idea of time to even have a definition of motion through space. So what does this mean? This is puzzling because time is required in order to define motion. So let me explain that last piece right there. What is motion? What is it for something to move, like through space? For example, I'm going to move this pen from point A right here to point B right there. Like, okay, so let's watch that happen. All right, it moved. Wow. Now, what just happened? Well, the pen, the marker, whatever, for it to go from point A to point B, for it to move, it has to be what? It has to be in different places at what? What does something have to do to move? In order for something to move, it has to be in different places at what? That's a question for you. You just answered. Yes, different times. For anything to move, by definition, that means that it has to change its position over time. If something's in the same place for all time, is it moving? Like if this pen stays in this place for the rest of time, is it a moving pen? No. It's a stationary pen then. It's a motionless pen. So for something to move from point A to point B, it has to change its position over time. It has to be in different places at different times. Like at this time, it's in this place. At the next time, it's in this other place. If it stays in one place the whole time, it's standing still. But notice that for me to explain to you what something has to do to move, I had to make a mention of time itself. There's no there's no analysis of motion that makes sense without reference to time. So now we're in a bit of a puzzle, because when you say that time moves, okay, well, what's motion? Motion is being in different places at different times. So if time itself moves, that's like saying that time is in different places at what? If time moves, then given the analysis of motion that we seem to have, that gives us a sort of circle. It's like time is moving by being in different places at different times, but time is the thing being analyzed, so we can't refer to it in an analysis of itself. What is this second order sort of time within which time itself is moving? That's really hard to understand. And to further reinforce why this is puzzling and paradoxical, he gives us a little graph to look at. Okay? So let's just look at a graph of physical motion through space, and then we'll show why this analysis breaks down when it's time that we're trying to understand how it moves. Okay, so this graph is shown in the book on page 458. So ordinary objects move with respect to time, and let's show that by means of this graph. So we can have 4 horizontal lines, and what we're trying to showcase here is the movement of a train which departs out of Boston and arrives at a final destination in Washington, D.C. So I'm going to place the names and labels of 4 cities beneath the bottom of each of these 4 horizontal lines. So it's Boston, New York, Philadelphia, Washington. Okay, and now T1, T2, T3, T4. So this little letter, lowercase t with a subscript, is just supposed to be a time designation. So the number of the subscript indicates the ordering in sequence. So this is like the first time. This is a second subsequent time. This is a third time that's further on after the second one, and this is a fourth and later time that follows after the third one. So let's say that this train moves from Boston to Washington by starting at initially in Boston. Later on, after that, it's now in New York as it travels. And later on, after that, it's in Philadelphia as it continues its journey. And finally, fourth, it arrives out there in Washington. So what we're showing you is that for this train to move, it has to be in these different places at these different times. If I have a different graph, which just shows the train Boston, 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 at all the 4 times, time 1, 2, 3, and 4, did that train ever leave? Did it ever move? No, that's the train that didn't ever move or leave the station. If it stays in Boston all the time, then it's not a moving train. So for it to be a moving train that moves, it has to have a different position at these different times, okay? But what does it mean to say that time itself moves? Well, one way of trying to define that is to say maybe it means that the present moment is moving. Maybe that's all that is meant. Maybe what we mean when we say time moves is that the present moment just does not sit still. So like, for example, what time is it right now? It's 9:39 and 55 seconds. So it's about 9:40 a.m. on October 30th of 2020. So right now, this is the present moment, right? But was this the present moment earlier this morning, like when you woke up? No. Back then, this was the future. But now, it's no longer the future because it's happening. And when you woke up this morning, now that's the past. That's no longer the present. But notice how the present keeps kind of changing around. When you woke up this morning, you're like, now this is happening. I'm waking up. This is the present moment. Now you're attending a lecture, and this is the present moment. And then later on today, when you're looking back at this is going to be the past. And then you're going to be doing whatever you're doing later, and that'll be the present moment. So it looks like maybe the present is the thing that moves, or at least he attempts to say that. But you'll see that in a moment he just says, never mind, that still doesn't work. But some would try to define or explain the movement of time by saying that the present is moving. But now he shows us that this is still just circular, and it really doesn't give us any kind of coherent understanding. So I'm going to change this graph around, or actually just create a new graph, which will allow us to sort of examine this proposal that the present moment is moving, and that's what is meant by the so-called movement of time. So this is figure 2 in the article, which is on page 459. Once again, we're going to have these 4 horizontal lines. Except in this case, instead of the labels for 4 cities, we're going to have 4 different times of the day. So let's say this is noon, this is 3 p.m., this is 6 p.m., and then this is 9 p.m. Okay? Okay, so maybe this is the proper graph to explain our puzzling question. What do we mean when we say that time moves? Maybe it's like this. The present moment is moving around always. So maybe this is the idea that, for example, at one initial time, noon is the present moment. So like later today when it's noon, 12 p.m. and like 2 hours and 18 minutes, whatever you're doing at that point, that'll be present. Then later on today, at 3 p.m. in the afternoon, that'll be the present moment. And then at a subsequent later time, say 6 will be the present moment. And then later on, even after that, 9. So maybe this expresses the movement of time because the present moment is moving. But Sider says, not so fast, actually. There's still an issue. There's a problem with this here graph. There's something about this graph that makes the graph go kind of in a circle and refer to time yet again. I wonder if anyone has a thought about what's wrong with this graph. Any guess? There's something about it that sort of is circular, basically. Just if you look at it, maybe you'll see something there that is undefined. Any thoughts? It's okay to take a minute, just pause and think about it for a minute. Let's see if you have any ideas. If you don't, that's okay. Well, because it goes back to 12 again, no, that's not it, Drew, because the subsequent 12 is going to be another moment 12. I mean, it's not the same day. Like 12 p.m. tomorrow is not 12 p.m. today. It's 12 p.m. on October 31st, 2020. So that's not the issue, but it's a good attempt. What else? That's not exactly what I meant by circle, like it just loops like that. I meant instead like it refers to a concept that is trying to be explained. Is it because if we were talking about time and the numbers are arbitrary? Well, that's a very deep and heady point, and there's some truth to that, yes, but not exactly the conceptual circularity that we're looking at here. It's okay, but if anyone wants to make one more little quick attempt, it'll be easy to understand once I say it, but if you have something, throw it out there. I guess I'll just try and mention it really fast. So the problem is these 4 coordinates on the left. What are these 4 coordinates? T1, T2, T3, and T4. It looks like these are time coordinates. And so what we're saying is that the present moment is changing its position by being in different places at different times. But now we're just saying time is moving through time. And that's a circularity. If time is moving through time, then ask this new question. How are these 4 things assigned in the order 1 through 4? What gives them that linear sequence? In order for them to be positioned with some temporal order, they would have to be placed within an even broader context of some 3rd order sort of time. And this would just lead us towards what we've called an infinite regress. Like, so if time can only be defined as moving because it's moving by being in different places at different times, then the time within which time is moving has to be assigned some kind of ordering. And that can only be given by referring to a tertiary time frame. And this just leads us nowhere. We can't just say time moves by being in different places at different times, because time is what we're trying to explain, and if we refer to it in its own explanation, then that is circular. So we really can't answer this question, he says, how to explain the concept of time moving. And so he has a new proposal. And here's the proposal that he suggests to get us out of this whole issue. Let us just instead, he says, embrace the space-time theory of Einstein. Because in Einstein's space-time theory, the whole idea that time passes and that there's motion to time and that there's a linear order is just all false. According to Einstein's theory of space-time, There's no movement to time. All the moments exist. There's really no such thing as the present or past or future. All of those moments are equally real, and none are more or less real than any others. So if you embrace and accept the implications of the space-time theory of Einstein, you no longer have this difficult task of trying to explain how time moves, because you basically just give up and say, you know what, it doesn't move. There's no movement to time. It just sits there and it contains all the events like a big block. I've heard this referred to in other philosophy articles as the block universe theory. Like, so the universe and everything in it, all the events, everything from the past, present, and the full future, they're all just contained and they're all equally real in this big space-time structure. And there's no becoming, there's no going out of being. Everything exists, it's all there forever, and all the events are equally real. So if you say this, then we no longer have the difficulty of explaining how time moves, because we just abandoned the whole concept that time moves, and instead we say it's an illusion, the perception that there's any movement to time. But even though that solves one problem, it kind of also opens up other issues. Like, so if time doesn't move, then how are we supposed to understand the nature of objects and even ourselves in the idea of a metaphysical universe where there's no movement to time? That's the next step to go over as we continue reviewing the work of Sider. So I don't want to rush through that, because it's going to take a few minutes to explain. But on Monday, we'll finish up this rest of the Ted Sider article. So just read him, and other than that, have a nice weekend. As I've said to you, I am almost finished with the midterms, and they will be done this afternoon. And I'm going to send you guys the announcement so that through the weekend and into next week, you'll be able to check on your score with me. So let's leave it at that for now, I guess. Does that sound good to you guys? Are we all on the same page? Let me know in the chat if so. Cool, thanks a lot. All right, so yeah, be in touch with me. I didn't get a chance to send off my office hour. Yeah, you'll email me to get the scores. That's right, Megan. And I'm going to announce in the message to you guys that that's the way I would prefer for you to request your score, so that I can tell you any comments and give you some feedback too. Okay, yeah, so thanks again, everybody. Happy Halloween. I don't know if anyone's actually going to be doing anything, but even if you're just walking around in your apartment or something with a costume, that's going to be kind of fun. I have to go to like a Zoom faculty Halloween thing for another campus that I'm teaching at. I don't even really have a costume. I used to have like a big costume that looked like a giant hamburger or something. That was really fun, but I don't know what happened to it. I think I let a friend borrow it and they never gave it back. So anyways, yeah, have a good Halloween, have a great weekend, and I'll be in touch with information about your midterms later today. All right, have a great one. Bye-bye.